Hi everyone. Today we're going to continue on 7.4. So last video we get to talk about Jacobi theorems. Oops, right here. And in the Jacobian theorems, we learned that we can actually transform an integral in one coordinate system to another coordinate system by performing the following, corresponding the regions together. So R would be the region in the new coordinates, and you have to, after transformation, become the regions in the original coordinate system. So here the vector x basically just means x, y, z, while the vector u could be the new coordinate system, just like polar or cylindrical or spherical or any coordinate transformation that we want. And we already know that we should perform a composition with the function f with the transformation that will allow us to now input the new coordinates into our function. And the new thing that we have to figure out is that the correspondence between the two set of differential is actually given by the absolute value of the Jacobian determinants. And we actually spent last video talk about the Jacobian determinant for the polar and the spherical coordinate system, and it wound up having the expression that we know already from the formula. So now what we're going to try to figure out would be the following, is how to actually use the theorems. Oops. So we have a very simple example that I want to show you. So here we go. So here's our first example. So it meant to be very straightforward, and I want to show you some of the important things that you need to be able to figure it out. So let's start with the following. So let's say let P be a parallelogram with vertices 0, 0, 2, 0, 3, 1, and 1, 1. And what we'd like you to do is to find the integral over P of x plus y dA. And I'm going to be, now since we talk about integral in different coordinate system, I'm going to say dA x sub xy, meaning I'm talking about dA in the xy coordinate system. So that would be basically dx dy by applying Jacobi theorem. And I will define the transformation for you with transformations. I'm going to define the transformation for you. T of uv is equal to u plus v. V, that's equal to xy. So of course in this scenario right here, we're defining the xy as our vector x, and then our uv is our vector u. So we start with our xy coordinate system, and I want you to rewrite it into the uv coordinate system, following by this transformation. Okay. So one interesting thing about it is that this transformation right here is actually called linear transformation. So it basically doesn't turn things into curve. It keeps everything straight line, but just changing those lines to different look. So instead of the xy coordinate system where x and y are perpendicular to each other, and one is horizontal, one is vertical, after this linear transformation, some of those lines would no longer be horizontal or vertical, and they no longer be perpendicular to each other. Now on your test, when I ask you to apply Jacobian theorem, I will give you the transformation that you need to use, so that way you won't have to worry about figuring that out. So according to Jacobian theorems, what we need to do is change three things: integrand, differential, and region of integration. So let's go through all three of them. So the first thing I need to do is, is to change the integrand. So that's probably the easiest thing to do, is to simply just do the plug in the transformation. So our function based on our integrand would be f of xy equal to x plus y. So now what I have to do is just do f of t of uv. So basically require me to plug in x in terms of u and v, which in this case, you can see that this basically tell me that x equal to u plus v and y equal to v. So therefore, x plus y, the x will become u plus v plus y, which is v. So therefore, that just come out to be u plus 2v. So that would be our new integrand, plain and simple. Next thing we need to do is the differential, which is also very straightforward also, because we know that t of uv is u plus vv. So therefore I can say that t prime of uv will just equal to 1, 1, 0, 1. And so now I can find the Jacobian determinant, which is determinant of t prime. And I do need the absolute value of that just to make sure that I don't forget. So that just turned into the absolute value of the determinant of 1, 1, 0, 1 is just 1. So therefore just 1. So that's nice. So therefore this implied that dx dy is just equal to 1 du dv, or basically just mean dx dy equal to du dv. So in this case, basically telling me that based on the Jacobian determinant, these two transformation actually does not change the area. And so therefore, the dx dy and du dv are actually come out to be the same exact area, which is nice. So now come on to the hardest part of the problem, and that is to deal with our regions of integration. Now, you might be thinking like, well, why would that be the hardest part? Well, the reason why this is the hardest part because the following. We need to integrate in uv. So therefore, I need to define the region of integration in uv. The problem? We don't have that. We have the regions defined in x and y. And we have a transformation, but the transformation only allows me to go from uv to xy. So therefore, the issue here is that we have the output already. We have the xy. We don't have the uv. That's the problem in trying to identify the region of integration. So therefore, what you need to do is to do the following. So first I'm going to do is try to look at what does this region of integration look like in xy first. So therefore, we'll look something like this. It would be 0, 0, 2, 0, 3, 1, and then 1, 1. So it seems to me that this is our parallelogram P. Oops, I missed that line. P. So that's in XY coordinate. What we need to do is kind of figure out what is the UV shape that would actually give me that. That's the issue. So how do we figure it out? So what you probably want to do now, in this case, necessarily not that necessary, because I know that the transformation is what we call linear transformation. So lines still remain to be line, just move over or changed over. So I could actually take the shortcut and just try to figure out what happened to these four corners or four vertices. But I am going to show you exactly what you're supposed to do. So in case if you have coordinate transformation that's not linear transformation, but like curvilinear transformation, you still have an idea as to what you need to do. Okay, so let's start with the following. The first I'm going to do is this. If I look at this parallelogram, I can recognize that this parallelogram is actually formed by these four lines. So if I can find out what happened to these four lines before the transformation, then I will know exactly what the regions that going to be in UV going to be. So therefore, it requires several things that we need to do. Number one, what I need to do is to figure out what is T inverse. Because if I know T inverse, or T inverse of XY, I'm sorry, that will be able to actually put in what we know in XY and form what I need in UV. And two is I also need to know how the regions are being bound, which is basically what these four lines are. Okay, so let's start with work on the T inverse first. How do I find the T inverse? Very simple. What I'm going to do is I'm going to take what I know and try to see if I can rewrite it by solving for U and V. And that way I will be able to rewrite the relationship backward and form our inverse. So this is pretty easy because we already know V equal to Y. So that means they're exactly the same thing. And because V is equal to Y, I can now say U plus V instead of V. And we'll say Y equal to X. And therefore tell me that U is equal to X minus Y. And so now these two equations allow me to define UV as a function of X and Y, and which is what our inverse function is designed to do. So I can now define my inverse function to be so that's my inverse function. Now I have a way to go from xy to uv, so that I can use the regions that we know in xy and try to map into uv. So the next thing I need to do is to understand how to define the regions P, so I can find out what regions I need in uv to plug in and to find P. So let's go for that. So if I look at this picture correctly, I notice that I have y equal to 1, y equal to 0, and I have these two kind of diagonal lines. It shouldn't take you too long to figure out the equation. The first one is pretty easy, is y equal to x, and the second one is also pretty easy, is y equal to x minus 2. Okay, they have a slope of 1, just have a different y-intercept. So now the question is, what happened to these four lines in the UV plane? So essentially what we're looking for is what in UV would form this four line. And the way to figure it out is to use our inverse transformation, so I can naturally plug in what we know in XY and hopefully figure out what it should be in UV. So let's try that, okay? So let's start with the first thing. I'm going to just go for each one of these individually. I'm going to just go with, how about y equal to 0, y equal to 1. So what happened to y equal to 1? So therefore, I would basically form tangent inverse of x1. And therefore, it will come out to be, based on what I have, x minus 1, 1. So the question is, what is that? Well, notice that that is actually a parametric representation. So I'm going to go and separate it. So I'm going to pull out an x, and now I have the vector 1, 0 plus negative 1, 1. So therefore, basically tell me that in this UV plane, this y equal to 1 will actually form the line that go through the point negative 1, 1 and go 1, 0. So let's draw that. So that would be this line right here. Negative 1, 1. So let's say here's 1, here's negative 1. So here's negative 1, 1. And then it would go 1, 0, which is basically going to the right only. So that actually will form this line. This line would be what y equal to 1 look like, which technically speaking is exactly the same. And it kind of makes sense because y and v are the same in a sense. Now let's see if we can do y equal to 0. So therefore I'm going to put in inverse, our t inverse of x 0, because y is 0. And therefore that becomes just x 0. So therefore I'm just going to say x 1, 0. So therefore indicate that this is a line that go through the origin 0, 0 and just go completely horizontal. So that's what y equal to 0 look like on the UV plane. Okay. Now, the next two are a little more complicated, but we can still figure out. So let's say y equal to x. Then basically what I have, it would be just xx. And therefore give me this line. So therefore it will be a line that goes through 0, 0, but goes 0, 1 as the direction. Okay. So 0, 1 would basically just mean no left and right, but just straight up. So therefore it would just be this line right here. So this is how the line y equal x will look like in UV. And now let's do the last one, y equal to x minus 2. So that means that we're doing tangent in the transformation T inverse of x, y, which is x minus 2. So therefore become x minus 2 and x minus 2. So notice how actually will subtract out the x and just leave you with a positive 2, x minus 2. Therefore you can say that's x times 0, 1 plus 2, negative 2. And so 2, negative 2 would be probably somewhere over here. Somewhere over here. And then it goes 0, 1, meaning it goes straight up and down. Oops, minus 2. And now it should be clear that this is the regions that we're looking for. This is what P would look like on the UV plane. And now is it surprised they come out to be a nice simple rectangle? No, remember, we're doing change of variable mainly to try to make a region into rectangular region, which clearly this transformation turned the parallelogram P into rectangular regions right here, which I'm going to go and call R. How's that? So now I'm ready to form my integral. And now that I have everything I need. So therefore my original integral is integral of P of x plus y dx dy. That's what dA x sub xy would be. And based on Jacobian theorem, that would mean that now I'm integrating over R, because R is the corresponding regions to P. Yeah. Okay. And we need to change the integrand. X plus y turn into u plus 2v. And then dx dy actually turn to 1 du dv. And yes, I don't have to write a 1 there, but I'm just going to do that just to remind, just to show you that that's something that had to happen there. But just in this case, it just happened to be 1, so we don't actually technically have to write it. And now I can then take this Riemann integral and now rewrite into iterated integral, because R is just a nice simple rectangle. So I'm going to go and say, if I look at this correctly, this horizontal y equal to 1 technically is the same as v equal to 1. And this horizontal line will simply be at v equal to 0. This vertical line y equal to x actually turned into u equal to 0. And this vertical line x minus 2 actually turned into u equal to 2. So those are the 4 lines that we use to bounce in R. So I'm just going to use that. So u equal to 0 to u equal to 2. V equal to 0 to v equal to 1. U plus 2v du dv. And this integral should be relatively easy to evaluate. I believe the answer is 4. You should go ahead and try to evaluate that to make sure that you get the correct answer. I think it's 4, but I could be wrong. If I am wrong, just make sure you make a note for that and just let me know during class. Okay? So that's basically the outline of how to do a change of variable problem. Change the integrand by forming the composition. do the differential by finding the Jacobian determinant and take the absolute value of that and use that to correspond to the differential together. The most difficult part will be this part right here, where you try to kind of reconstruct the proper regions for the integration in the coordinate system that you want to use from the coordinate system that you're given. And that usually will be the part that most students get stuck on. So that will be the part that you want to focus and make sure you know what to do. Now, before we do another example of this, I do want to actually show you this example, which is, I actually talked about it before, is that we can actually use a change of variable method to actually evaluate and find a four-dimensional sphere volume. So I'm going to go and try to do that. Now, I don't know if I have enough time to actually go through the problem because it is not an easy problem to go through, but I'm hoping to start this process, and I'll probably go end the video roughly about 30 minutes or so and then finish up on the next video. Okay, so let's at least start the process. And if you feel confident that you can figure it out wherever I left off, then obviously go for it. So here's how to define a sphere in R4. Let x squared plus y squared plus z squared plus w squared equal to capital R squared be a sphere in R4. With radius capital R. Okay, so we don't know what R is. R could be 1, or could be 4, or could be whatever it is. I'm just want to find a general formula for the volume, which is the reason why I just keep it generic R. So what I want to do is find the fourth dimensional volume of this sphere. And of course, as you probably remember from your take-home test, it's actually not possible to evaluate this fourth dimensional sphere volume the way that it is in the x, y, z, w coordinate, because the integral is actually extremely difficult to do. So what I'm going to do is we're going to use Jacobian theorem, of course. But of course, we will need a proper transformation to do that. And lucky for you guys, I have just the one that we can use to figure this out. So Jacobian theorem with the transformation right here. This transformation actually has a name. It's often referred to as a double polar coordinates transformation, which looks something like this. T of P alpha Q beta is equal to P cosine alpha, P sine alpha, Q cosine beta, Q sine beta, which is equal to X, Y, Z, W. So notice that you literally, as the name suggests, it's just two separate polar coordinates. One set for xy, which is p cosine alpha, p sine alpha, and another set for z and w, which is q cosine beta and q sine beta. Here's the domain for the function, along with the domain, which is p go from 0 to infinity, but not include 0 because of, once again, 1 to 1. Alpha can go from 0 to 2 pi, but not include 2 pi because that's the same as 0. Q can go from 0 to infinity, and beta go from 0 to 2 pi. So once again, it's just basically the polar coordinate system, but just using two of them at the same time. So the question then is, how do we use this to figure out the volume? So it's pretty simple. This is how. So first of all, we need to understand is that I'm going to go and call this sphere S, which I'm going to write that right here. I totally forgot. So how do you find the volume of this sphere? Well, simple. Just a Riemann integral over S dv in the x, y, z, w coordinate system. And I will write out the how this integral look like in the XYZW system, but of course, because that actually was one of the test questions, I'm not going to go do that. So hopefully you figure that one out on your own. So now the question is, how do I rewrite it into the double polar coordinate system? Well, number one, because I'm just finding volume and there's no integrand, so one less thing to worry about. I do need to find out what happened to differential and also what happened to our region of integration. So let's go and do that. So how do I find out what is the coordinate, how is the differential related? Well, Jacobian determinant. So I'm going to go and find our Jacobian determinant. So I'm going to leave room here for my integral. So first, next thing I'm going to do is I'm going to try to find my Jacobian determinant and take the absolute value of that. So let's go ahead and do that. So let's see, what is T prime? So T prime is actually a 4x4 matrix. And it might sound complicated, but actually pretty easy. If I take the derivative of P, I get cosine alpha. If I take the derivative with alpha, I get negative P sine alpha. But if I take the derivative with respect to Q, it would just be 0. And if I take the derivative with respect to beta, it would just be 0. And if I take the derivative with respect to alpha, I get sine alpha. And then take the derivative with respect to P. I'll take the derivative with respect to alpha, I will get P cosine alpha. And then, once again, there's no Q or beta. On the flip side, the last two coordinates have no P, no alpha. But if I take the derivative with respect to Q, it becomes cosine beta. And then with beta, it will be negative P sine beta. And then this will be sine beta. And then P cosine beta. And if you look at this matrix right here and you're like, wait, that look kind of familiar. Of course it does. Because it's basically just the two polar coordinate Jacobian matrix kind of put together to form this 4x4 matrix and by filling all the zeros. So what is the Jacobian determinant for this thing? So because I have the 2, 0, it actually make it pretty easy to do. I'm just going to do this. I'm going to say this is just cosine alpha times the determinant of P cosine alpha, 0, 0, 0 cosine beta, negative P sine beta, 0 sine beta, P cosine beta, plus, or actually minus, I guess. Well, actually it's minus the next one, but because it's negatives, so it's double negatives, so we become plus P sine alpha multiplied by the determinant of sine alpha 0, 0, and then 0 cosine beta, sine beta. I'm gonna need a little bit of room. There you go, just a little bit is good. And then 0 negative oh, these two are Q. Now I'm like, wait, why is it P again? So that fixed these two to Q. My mistake. And then these two are, oh, that one is Q. I already writing the Q. That's how I figured it out. I was wrong. And Q cosine beta. So now these two are both triple 3x3 integral. I'm talking about determinant. But lucky for us, because all the zeros involved. So therefore, now I can actually kind of put it together and say, oh, that's just equal to cosine alpha multiplied by P cosine alpha multiplied by AD minus BC, so become Q cosine square beta minus, but this has a negative, so become plus Q sine square beta plus P sine alpha multiplied by sine alpha multiplied by AD minus BC become Q cosine square beta plus Q sine square beta. Now I know it does look like a lot of complicated thing, but actually it's not, because if you look at this right here, this just multiplied to Q. Because you factor Q, you have cosine square beta plus sine square beta, that's 1. And happen to the same thing over here, that just factor out to a Q. And so now if I look at what I have, I actually have PQ cosine square alpha plus PQ sine square alpha. And notice that's the exact same thing that we just did. I can just factor out PQ, and then the cosine square and the sine square alpha just go away. And that gives me our Jacobian determinant. And I don't need the absolute value because P and Q are by design to be positive real numbers anyway. So therefore, what does that tell me is this. Oops, wrong direction. What does that tell me is that the Jacobian determinant is PQ, therefore implying that dx, dy, dz, dw would just equal to PQ, dp, d alpha, dq, d beta. So that takes care of our differential. Unfortunately, it's already past 30 minutes, and I told you that I will stop at around 30 minutes. So we'll continue this example in our next video. Okay, talk to you guys later. Bye-bye.